So hi everybody, welcome to this talk. So this is joint work with Amay Bangale and Subhash Kort, and this talk is about on approximability of satisfiable CSPs. So this is a line of work with the goal is to study the approximability or inapproximability of satisfiable instances of CSPs. So let's start with defining what are the objects that we study. So the main object of study is constraint satisfaction problems, and to define them, let's start off with a few simple examples. So the first of which is the three-sat problem, which I hope that most of you have seen at some point in life. So here is a definition of three-sat, but it's going to look a bit different from the way it usually is presented, but it's really the same. So we have a predicate, P, which takes as input 3 bits, and outputs 1 bit, which you can think of as yes or no. And the output of P on input X, Y, Z is 1, if and only if at least one of them, at least one of the inputs is 1. And with this predicate in mind, an instance of 3-sat consists of a set of n variables, x1 to xn, along with a bunch of constraints, and each constraint is the predicate P applied on 3 variables, some of them can be negated, is equal to 1. And usually, when you talk about 3-sat, you care about satisfiability. Namely, I give you this list of variables and constraints and ask you, is there a Boolean assignment to the variables that satisfies all of the constraints? Okay, so this is 3-sat. Now let's go to yet another very fundamental problem, which is called thrilling, and we're going to present it in the same style. So it's really the same, except that the predicate P now is different. So in this case, the predicate P again takes 3 bits as the input, but this time you should think of these 3 bits as elements in the field of size 2 in F2, and it outputs 0, 1. And the predicate applied on P, X, Y, Z is equal to 1 if and only if the sum of X, Y, and Z in the field of size 2 is 0. Okay, so with this predicate in hand, an instance of thrilling consists of a set of variables x1 to xn, and again, a bunch of constraints which are P applied on a bunch of variables, and some of them can be negated. And the constraints are always that P is equal to 1. So again, you ask about the satisfiability of thrilling instances. I give you an instance and ask you, is it satisfiable or not? So what can we say about the complexity of these problems? Well, 3-sat, this is the famous Cook-Levin theorem, is NP-hard. And this is the most basic result that you have in complexity theory. And thrilling, well, thrilling is a problem that we know to be solvable in polynomial time. This is one of the most basic facts in linear algebra, and this follows because you have Gaussian elimination. So you can apply that, and if an instance of linear equations is satisfiable, you're going to find a satisfying assignment. So very broadly speaking, what we're trying to do in this work, and in general in this line of works, is understand what makes 3-sat hard while making thrilling easy. More generally, well, it doesn't quite make sense to ask this question because 3-sat and thrilling are very concrete things, so you can come up with a whole bunch of reasons for that. So what we're really after is about general theory. This is something that has been well studied for a long time. And what we kind of do new in this line of work is insert the length of approximation. Is there some version of hardest of approximation that makes problems either BNP or NP hard? Okay. So we've seen 2 examples, but now we can define CSPs in general. So given finite alphabet sigma, you should think of the size of sigma as constant, and an array parameter k, which you can think of constant again, k equals 3 is good enough for us. So given this predicate, we define the problem CSPP as follows. So an instance of psi is composed of variables x1 to xn, along with a bunch of constraints, which are P applied on k of the variables equals 1. And there are many variations that you can think about. Some of them involve more than one predicate, some of them involve negations, not negations. I'm going to focus on this very specific thing because it makes life a bit easier, but we can extend the theory beyond that. So with this in mind, the problem of satisfiability asks, given an instance psi that is promised to be satisfiable, can you efficiently find a satisfying assignment? So what's the computational complexity of this problem of finding a satisfying assignment? Well, in 78, Scheffer proved in a very nice work that for every constant k, and once you take the alphabet sigma to be Boolean, namely 0 and 1, then it is true that for every predicate p that you choose, this CSPP problem must either be in P or else it is NP hard. Namely, there is no P which is giving you an intermediate problem. So we know that intermediate problems exist, but the main point of this theorem is that the satisfiability of CSPs cannot be something that weird. It's either NP or NP hard. So following Scheffer, it took Federer and Vardy 20 years to conjecture that this dichotomy behavior of either being in P or being NP hard holds not only for Boolean alphabets, but for every finite alphabet. And they raised it, and this was called the dichotomy conjecture. And it took some time, but eventually this was proved independently by Zook and Bulatov, and they proved that for every predicate P on any alphabet whatsoever, CSPP is either in P or is NP hard. So what can you say about approximation version of CSPP? So the main goal of this line of work is to establish a version of the dichotomy theorem for approximation problems. And in a nutshell, what you have to do here is have a result that sort of combines the considerations from the dichotomy theorem with another prominent result in complexity theory called the Raghavendra theorem. So we're going to talk about this soon, but really you're trying to gain the best of both worlds from these two very nice works. So what is Raghavendra's theorem? Well, this is the following statement. So it asserts that for every finite alphabet whatsoever, and for every arity k, for every predicate p, there is some number alpha such that if I give you an instance psi of CSPP, which is promised to be 1 minus epsilon satisfiable, by that I mean that you can satisfy almost all of the constraints of the instance psi, then there is an algorithm which is an alpha approximation, namely an efficient algorithm that finds an assignment that satisfies at least alpha fraction of the constraints of psi. And moreover, alpha is the best you can do. Namely, if you try to get alpha plus delta approximation for some positive delta, then this is already NP hard. And you can see that there is some asterisks here, and this is because this is not really NP hard, it's only NP hard assuming the unique conjecture, but I'm not going to talk about UDC at all in this talk, so let's ignore that for the moment. So the Raghavendra result is really beautiful. It even gives you the algorithm for, in the algorithmic case, which is some natural semi-definite program relaxation of the problem, plus Gaussian rounding scheme. And at this point, you might ask, okay, Raghavendra is very nice, is dealing with instances that are almost satisfiable, namely 1 minus epsilon. So what's the big difference? Almost satisfiable, satisfiable, what can even happen? It's really, it's a little epsilon. But there are sometimes differences, and sometimes they are very, very big. And in fact, we've already seen one such difference. So if you look at the 3-line problem, if I give you an instance which is fully satisfiable, well, you can solve it in polynomial time. But if I give you an almost satisfiable instance, the best you can do is something trivial. The best you can do is satisfy half of the constraints. And this is a well-known result of Hustle. So, this little epsilon in the promise made a huge difference in the algorithm that you can achieve. And the question is, when such a big difference can exist and what governs it? But this is also not always the case. So for PSAT, it's the same both in satisfiable and almost satisfiable. So it's not like there's going to be a huge difference for every single problem. So something has to happen for that. And for the remainder of the talk, we're going to focus on K equals 3. So here is our conjecture, and this is what we conjecture that should happen. So we conjecture that for every finite alphabet sigma, and for all arity k, and for every predicate p, there is still some alpha between 0 and 1, such that if I give you an instance of CSPP which is promised to be fully satisfiable, then there is an algorithm that achieves an alpha approximation, but doing anything slightly better is NP-hard. Namely, we really conjecture that what holds in Radoventri's case should also hold here, except that this is in the satisfiable instances case. And of course, CSPP has to be NP-hard by itself. Otherwise, this theorem has no content because you can just fully solve it. But, so this is the conjecture. And one key step in the proof of Rajavendra was that he was able to come up with the algorithm and then show that the performance of it matched the hardness. But in this case, we don't really know what the algorithm is. We know that it cannot be an SDP-based algorithm because SDPs cannot really solve linear equations. We know that you have to have some form of Gaussian elimination, but this is not always the solution. Sometimes you have to do SDP. Maybe you have to do some linear program, who knows? So probably what you have to do is combine all of them in some smart way, and this is something that indeed we suspect is happening, and we have some preliminary results about it, but for now we don't really know. And this is a long-term goal. The economy conjecture took 20 years to prove, or the Mandra took around 15, so this is nothing is going to happen too soon, but I think that there is a lot of things that are going to be understood on the route to proving this conjecture. So this is generally about this line of work, but now let me tell you something specific about this precise paper. So the main result of this paper is for an analytic result that is directly motivated by this conjecture, and namely the interplay between the algorithm and the harness, and this is a purely for analytic statement that actually has applications elsewhere. So here is the main analytical problem. Suppose I give you 3 functions, complex valued functions, that are one-bounded. And each function maps a string from sigma to the n to a complex number, and the output of FGNH is always at most 1 in absolute value. Now, additionally, I give you mu, a distribution over sigma to be 3. When can it be the case that FG and H have a correlation according to mu? Namely, I sample x, y, z, where each coordinate xi, yi, zi is distributed independently according to mu. I apply f, g, and h, I take a multiplication, and I get that the expectation of all of this business is at least epsilon. What sort of functions FGH can even do that? So here is an observation. If the support of mu is full, then each one of FGH must be correlated with a low degree function. In fact, the most basic case where the support of mu is full and mu is just uniform is very easy to see because the expectation of FG and H is equal to the product of expectations. So this can only happen when FG and H are correlated with constant function. If mu is not uniform, then this is a little bit more complicated, but it's still not very difficult to see that low degree functions is all that you can do. Now, a more advanced statement, and a very useful one by Mosel, addresses the case that the support of mu is connected, which is a weaker property than being full. And in that case, he makes the same conclusion that Fg and H must be correlated with a low degree function. So what is connected? So let me very briefly tell you what it is. So consider a bipartite graph whose sides are sigma squared and sigma. And you connect the vertex AB with the vertex C if ABC are in the support of mu. Then we say that support of mu is connected if this bipartite graph that we just drew is connected. So it's clear that if the support of mu is full, this is just a complete bipartite graph. So of course it's connected, but the converse is not full. So something can be connected but not full. So here is the main point that gets our work. So what happens now when the support of mu is not connected? Can we say anything meaningful about FGH at all then? So let's take something which is not connected. Here is a very instructive example. Suppose that the alphabet sigma is Fp, the field of size P, and take mu to be the uniform distribution over triplets XYZ that sum up to 0 over Fp. Then you can observe that this is not a connected distribution, because if you know what is x and y, you know what is z, so that graph is just going to be a matching. And if you do some Fourier analysis of Fp, you realize that Fg and H can achieve non-trivial correlation only if they are correlated with Fourier characters. And Fourier characters are usually not low-degree functions. So we see that when you go outside the realm of connected distributions, you're no longer looking after low-degree functions. You have to take Fourier characters into account. So what about general mu? In general, your alphabet sigma doesn't have to be some finite field Fp. It can be something completely abstract. But yet, at the same rate, you must sort of combine this type of considerations and the considerations that come from the connected case. So what can you even say? So here is the main result of this paper. So we prove that under some mild assumptions about the distribution mu, which I don't want to get into because it's a bit too technical, it's something that we call pairwise connected and not having Z embeddings. So you can look at the paper if you want to know what this is precisely. But model these mild assumptions, we show that if you have a distribution mu in functions Fg and H that achieve correlation like that, then there must be an abelian group G of constant size, as well as a labeling of the alphabet symbols from sigma by group elements. So let's call this labeling little sigma that maps big sigma to G. And there must be a Fourier character from this abelian group, and as well as a low degree function L, such that the function f is correlated with the low degree function L times the Fourier character after you adapt the input to be from sigma. In words, the functions f and similarly g and h must be correlated with a Fourier character up to multiplying by a low degree function. So you see that there is a combination of what's happening in the non-connected case and what's happening in the connected case. And this turns out to be all that can happen. So let me conclude this talk. So in this talk, I talked about the approximation dichotomy conjecture, which is the main goal that we have in this line of work. And I presented a key tool that we have in this line of work, which is for analytic stability result about free-wise correlations. So, I didn't have too much time today, but let me tell you that these results have much of other applications. So, for example, we managed to use this stability result in multiplayer parallel repetition, in additive combinatorics, in probability testing, and even more. And one sort of thing that is quite nice about it is that it turns out that you can generalize the invariance principle, which is very prominent in the study of approximation algorithms and hardest approximation, and actually something that extended is what is called the mixed invariance principle, and this is useful in our case. And I'll end by saying that three-ways correlations and the fact that they are much harder to study than pairwise correlations is something that happens in many other places, and it would be interesting to see if our techniques have any bearing on it. So I would be very interested to see if there are any applications in multiplayer communication complexity, pseudo randomness, quantum, all of that, and of course on the approximation dichotomy conjecture. And as concrete problems, I really like this full three-player parallel repetition theorems. There is something in combinatorics known as density health duet, and it will be very interesting to see if one can use these techniques to have any progress on getting effective bounds for this result. And finally, there's this dichotomy theorem, which we talked about in the beginning of the talk, which the current proof is completely algebraic. And it will be very interesting if, using these sort of considerations, we could get a different, more analytical proof for that. So that's all I have to say. Thanks.